Hello there, and welcome to the Slumber Lab, where the mysteries of the universe unfold gently beneath the blanket of night. Tonight, we're embarking on a quiet journey into one of the most profound puzzles that has ever captivated human imagination. We're going to explore the invisible architecture of our cosmos, the hidden scaffolding upon which galaxies hang like delicate ornaments, and the phantom matter that shapes everything we see, yet refuses to be seen itself. I'm so glad you've found your way here tonight. Whether you're settling into bed with a warm cup of tea, curling up on the couch after a long day, or simply seeking a peaceful moment of wonder, you've come to exactly the right place. This is your invitation to drift into the cosmic mystery of dark matter, that elusive substance that makes up most of our universe, yet remains as invisible as a whisper in the dark. Before we begin our gentle exploration, I'd love to know where in the world you're listening from tonight. Are you watching the same stars that ancient astronomers once puzzled over? What time is it in your corner of the cosmos? If you find this journey soothing or intriguing, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little corner of cosmic calm reach other wanderers who might need a peaceful pause in their day. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing something extraordinary about the invisible universe that surrounds us. So settle in, let your thoughts slow like distant starlight, and let's begin our gentle voyage into the mystery of dark matter. Imagine, if you will, standing in a vast library at midnight. The shelves stretch endlessly into shadows, filled with books you can sense but cannot see. You know they're there because of the way the light bends around them, the way the silence feels heavier in their presence, the way the very air seems to whisper of hidden knowledge. This is perhaps the closest we can come to understanding our relationship with dark matter, the invisible librarian of the cosmos. Dark matter is everywhere around us, threading through this very room as you listen, passing through your body, through the earth, through the stars themselves like a cosmic ghost that shapes everything, yet touches nothing we can directly perceive. It makes up roughly 85% of all matter in the universe. Think about that for a moment. Everything you can see, every star that twinkles in the night sky, every planet, every grain of sand, every cell in your body, all of it combined, makes up less than 15% of what's actually out there. The rest is dark matter, playing hide and seek on a universal scale. Scientists have been chasing this cosmic phantom for decades, building increasingly sophisticated instruments deep underground, launching telescopes into the cold depths of space, and creating theoretical frameworks that stretch the very limits of human imagination. Yet dark matter remains as elusive as sleep on a restless night, always just beyond our grasp, always one step ahead of our most clever experiments. The story of dark matter begins not with grand theories or complex equations, but with a simple observation that changed everything. In the early 20th century, astronomers began to notice something peculiar about the way galaxies moved. Picture a figure skater spinning on ice. When she pulls her arms close to her body, she spins faster. When she extends them, she slows down. This is because most of her mass is concentrated near the center of her spin. Galaxies should behave similarly. The stars at the outer edges should move more slowly than those near the center, where most of the visible matter appears to be concentrated. But that's not what astronomers observed. Instead, they found that stars at the edges of galaxies were moving just as fast as those near the center, sometimes even faster. It was as if the figure skater could extend her arms and somehow spin even more rapidly, defying everything we thought we knew about physics. This cosmic mystery deepened in the 1970s when astronomer Vera Rubin, working quietly in the darkness of observatories, began measuring the rotation curves of spiral galaxies with unprecedented precision. Her observations confirmed what earlier astronomers had suspected but couldn't quite believe. Galaxies were spinning far too fast for the amount of visible matter they contained. By all rights, they should have torn themselves apart long ago, flinging their stars into the cosmic void like drops of water from a spinning wheel. But they didn't. The galaxies held together, serene and stable, as if embraced by invisible arms. Something was providing the extra gravitational pull needed to keep these cosmic carousels intact. Something massive, something pervasive, something that could only be detected by its gravitational influence on the matter we could see. Scientists called this mysterious substance dark matter, not because it was necessarily black or sinister, but because it seemed to absorb, emit, or reflect no light whatsoever. The evidence for dark matter extends far beyond the rotation of galaxies. When astronomers peered deep into space with their most powerful telescopes, they observed something remarkable happening on the largest scales imaginable. They see galaxy clusters, vast congregations of hundreds or thousands of galaxies, bound together by gravity, and these clusters behave in ways that suggest they contain far more matter than meets the eye. One of the most compelling pieces of evidence comes from gravitational lensing, a phenomenon that Albert Einstein predicted decades before we had the technology to observe it. Massive objects bend space and time around them, and this bending can act like a cosmic magnifying glass, distorting and amplifying the light from objects behind them. When astronomers map this lensing effect around galaxy clusters, they find that the gravitational field is much stronger than what the visible matter alone could produce. It's as if the clusters are embedded in vast halos of invisible matter, dark matter that reveals itself only through its gravitational embrace. Perhaps even more dramatically, astronomers have observed collisions between galaxy clusters, cosmic crashes that unfold over millions of years. In these collisions, something extraordinary happens. The visible matter, the gas and dust that glows and can be detected by our instruments, gets slowed down and heated up by the collision, like two clouds of steam meeting and mingling. But the dark matter, interacting only through gravity, passes right through largely unaffected, like two groups of ghosts walking through each other in a haunted ballroom. These observations paint a picture of a universe where the visible and invisible dance together in an intricate cosmic ballet, sometimes in perfect harmony, sometimes pulling apart in ways that reveal the hidden choreographer. Dark matter appears to form the scaffolding upon which the visible universe hangs, providing the gravitational framework that allows galaxies to form, stars to ignite, and ultimately, planets like Earth to coalesce from cosmic dust. The cosmic microwave background, that faint afterglow of the Big Bang that still whispers across the universe, also bears the fingerprints of dark matter. This ancient light, stretched and cooled over billions of years, shows tiny fluctuations in temperature that correspond to the density variations in the early universe. These fluctuations are the seeds from which all cosmic structure grew, and the pattern they create can only be explained if dark matter was there from the very beginning, shepherding the formation of the first stars and galaxies. Yet for all the evidence of dark matter's existence, its true nature remains one of the deepest mysteries in science. We know it's there because we can see its effects, like deducing the presence of a master puppeteer by watching the marionettes dance. But what is it made of? How does it interact with itself and with ordinary matter? Why does it seem to avoid the electromagnetic force entirely, passing through us and everything else, like we're made of nothing but empty space? These questions have spawned a global hunt involving thousands of scientists, underground laboratories carved from solid rock, particle accelerators that smash atoms together at nearly the speed of light, and space-based observatories that peer into the furthest reaches of the cosmos. It's a detective story on a cosmic scale, where the criminal has left evidence everywhere, but remains frustratingly out of sight. Some scientists propose that dark matter consists of exotic particles that barely interact with ordinary matter except through gravity. These hypothetical particles might be relics from the early universe, created in the first moments after the Big Bang and still drifting through space like cosmic fossils. Others suggest that dark matter might be composed of primordial black holes, gravitational wells so deep that not even light can escape them, formed in the chaotic first seconds of cosmic time. There are even more exotic possibilities. Perhaps dark matter exists in what scientists call a dark sector, an entire hidden realm of particles and forces that mirror our own, but remain forever separate, like a shadow universe that shares our space, but never quite touches our reality. Or maybe the solution is even stranger, requiring us to modify our understanding of gravity itself, to accept that the force that keeps our feet on the ground and the planets in their orbits behaves differently on cosmic scales than we've assumed. As you lie there tonight, perhaps feeling the gentle pull of sleep beginning to tug at your consciousness, consider this remarkable fact. Billions upon billions of dark matter particles are likely passing through your body every second. They stream through you like cosmic rain, these invisible messengers from the depths of space, carrying with them the secrets of galaxy formation and the hidden architecture of reality itself. Yet you feel nothing, notice nothing, because they interact with the atoms of your body so weakly that their passage leaves no trace. This might sound unsettling, this idea that we're constantly bathed in invisible matter, but there's something rather comforting about it too. It suggests that we're more connected to the cosmos than we might imagine, that the same mysterious substance that shapes galaxies and guides the dance of distant stars is flowing through us right now, making us participants in the grandest mystery of all. The search for dark matter continues in laboratories around the world, in underground chambers shielded from cosmic rays, in particle detectors cooled to temperatures colder than the depths of space. Scientists wait patiently for the telltale sign of a dark matter particle colliding with their instruments, for that faint whisper that might finally reveal the nature of the universe's hidden majority. But perhaps the most beautiful aspect of the dark matter mystery is how it reminds us of the limits of human perception and the vastness of what remains unknown. In an age where we can sequence genomes and split atoms, where we carry the sum of human knowledge in our pockets and speak face to face with people on the other side of the world, it's humbling to realize that most of the universe remains invisible to us, as mysterious as it was to our ancestors who first looked up at the stars and wondered what lay beyond. Dark matter teaches us that the universe is far stranger and more wonderful than our senses alone could ever reveal. It suggests that reality extends far beyond what we can see, touch, or measure directly, into realms that require imagination, mathematics, and careful reasoning to explore. It's a reminder that the cosmos still holds secrets, still offers mysteries worthy of a lifetime's pursuit, still whispers of wonders beyond our current understanding. So as you drift towards sleep tonight, carried gently by the rhythm of cosmic mysteries and the quiet poetry of the unknown, remember that you are part of something vast and mysterious, something that extends far beyond the boundaries of the visible world. Dark matter flows around you and through you, connecting you to galaxies billions of light years away, to the very structure of space and time itself. The universe keeps its secrets well, but it also leaves clues for those patient enough to look, creative enough to imagine, and humble enough to accept that the greatest mysteries might be the ones that teach us the most about wonder, about curiosity, and about our place in the cosmic story that's still being written. Sweet dreams, fellow cosmic wanderer. So far we've explored how dark matter shapes our universe through its gravitational influence and examined the various theories about what these invisible particles might be. We've met potential candidates like WIMPs, Axions, sterile neutrinos, and even primordial black holes, each offering their own compelling explanation for the cosmic scaffolding that holds galaxies together. But the search for dark matter isn't just theoretical anymore. Around the world, in underground laboratories and cutting-edge facilities, scientists are conducting some of the most sophisticated experiments ever devised, all in the hope of catching a glimpse of these elusive particles. The quest to detect dark matter directly represents one of the most ambitious undertakings in modern physics. Think about it for a moment. We're trying to catch particles that barely interact with ordinary matter. Particles so ghostly that trillions pass through your body every second without leaving a trace. It's like trying to photograph shadows in a room full of mirrors while wearing a blindfold. And yet, scientists have developed ingenious methods to do exactly that. The landscape of dark matter detection is vast and varied, employing three main strategies that complement each other like instruments in a cosmic orchestra. There's direct detection, where we try to catch dark matter particles as they bump into specially designed detectors here on Earth. There's indirect detection, where we search for the signatures of dark matter particles annihilating or decaying in space, producing observable radiation. And there's collider detection, where we attempt to create dark matter particles in powerful accelerators and study their properties. Let's begin our journey into this experimental wonderland with direct detection, perhaps the most intuitive approach to finding dark matter. The concept is beautifully simple. If dark matter particles are constantly streaming through Earth, occasionally one might collide with an ordinary atom in a detector, producing a tiny but measurable signal. It's cosmic archaeology in real time, waiting for the universe's most elusive residents to knock gently on our door. The challenge, of course, is that these knocks are incredibly soft. If a WIMP particle interacts with an atomic nucleus, it might transfer only a minuscule amount of energy, barely enough to jiggle the atom. Detecting such subtle interactions requires instruments of extraordinary sensitivity, capable of measuring energy deposits smaller than what you'd get from a single photon of visible light. It's like trying to hear a whisper in a thunderstorm, which is why these experiments are conducted in some of the quietest places on Earth. Most direct detection experiments are housed deep underground, often in former mines or specially constructed caverns. The Sanford Underground Research Facility in South Dakota, built in an old gold mine, sits beneath a mile of rock. The Gran Sasso National Laboratory in Italy is nestled under a mountain in the Apennines. These subterranean sanctuaries serve a crucial purpose. They shield the delicate detectors from cosmic rays, the high-energy particles that constantly bombard Earth's surface. While dark matter particles can pass through rock as easily as they pass through empty space, cosmic rays are stopped by the massive overhead shielding, creating an environment quiet enough to listen for dark matter's whisper. The detectors themselves are marvels of engineering and physics. Take the Eludes Zeppelin experiment, or LZ, currently one of the world's most sensitive dark matter detectors. At its heart sits a tank containing 7 tons of ultra-pure liquid xenon, cooled to -100 degrees Celsius. This xenon serves as both the target for dark matter interactions and the medium for detecting them. When a particle strikes a xenon nucleus, it produces 2 signals, a prompt flash of light and a delayed signal from electrons that drift upward through the liquid. By measuring both signals and their timing, scientists can determine where the interaction occurred and how much energy was deposited. But here's where it gets truly impressive. LZ can detect energy deposits as small as a few keV, equivalent to the energy of a single X-ray photon. To put this in perspective, If the energy from a dark matter collision were a grain of sand, these detectors could spot it among all the beaches on Earth. The sensitivity is so extreme that the detectors can actually measure the tiny recoil of atomic nuclei when struck by individual particles, like watching a bowling ball gently nudge a marble. The xenon isn't just sitting there passively either. The entire detector is surrounded by layers of shielding and veto systems designed to distinguish genuine dark matter signals from background radiation. Photomultiplier tubes, incredibly sensitive light sensors, line the top and bottom of the xenon chamber, ready to catch the faintest glimmer of light produced by particle interactions. Sophisticated electronics and computer systems analyze every event, looking for the characteristic signature that would indicate a dark matter particle has finally revealed itself. And LZ isn't alone in this cosmic vigil. Around the world, dozens of experiments are taking different approaches to the same fundamental challenge. The Darwin collaboration is developing an even larger xenon detector, while experiments like CDMS and Super CDMS use silicon and germanium crystals, cooled to temperatures colder than outer space. Each approach has its own advantages and sensitivities, creating a global network of dark matter sentries, each one listening for a different note in the cosmic symphony. The remarkable thing about these experiments is their patience. They run continuously, day and night, accumulating data for years at a time. Scientists analyze millions of events, searching for the handful that might represent genuine dark matter interactions. It's a testament to human persistence and ingenuity, this willingness to spend decades and billions of dollars chasing particles that might not even interact in the way we expect them to. But direct detection is just one piece of the puzzle. Sometimes, instead of waiting for dark matter to come to us, we look for signs of its presence in the cosmos itself. This brings us to indirect detection, an approach that turns our telescopes into dark matter detectors, scanning the heavens for the afterglow of invisible particle interactions. The universe is vast, and dark matter is everywhere, which means that if these particles do occasionally interact with each other, those interactions should be happening constantly throughout the cosmos. Some theoretical models suggest that when two dark matter particles meet, they might annihilate each other, producing a burst of energy in the form of gamma rays, neutrinos, or other detectable particles. It's like watching fireworks in the dark. You can't see the fireworks themselves, but you can see the light they produce. This is where space-based telescopes and ground-based observatories become our eyes and ears for dark matter. The Fermi Gamma Ray Space Telescope, for instance, has been scanning the sky for over a decade, mapping the gamma-ray glow of the universe with unprecedented precision. If dark matter particles are annihilating in dense regions like the centers of galaxies or around black holes, they should produce distinctive gamma-ray signatures that Fermi could detect. The search for these signatures requires detective work of the highest order. Gamma rays can be produced by many astrophysical processes: supernova, black holes, neutron stars, and cosmic ray interactions, to name just a few. Distinguishing a potential dark matter signal from this cosmic background is like trying to identify a specific voice in a crowded stadium. Scientists must carefully model all the known sources of gamma rays and look for excesses that can't be explained by conventional astrophysics. One of the most promising targets for indirect detection is the center of our own galaxy, where dark matter should be most densely concentrated. The galactic center is indeed bright in gamma rays, but it's also home to a supermassive black hole and intense star formation, making it challenging to isolate any dark matter contribution. More promising might be dwarf spheroidal galaxies, small satellite galaxies that orbit the Milky Way. These systems are thought to be dominated by dark matter, but have relatively little star formation or other gamma-ray producing activity, making them cleaner laboratories for dark matter searches. Neutrino detectors also play a crucial role in indirect detection efforts. Neutrinos are nearly massless particles that barely interact with matter, making them excellent messengers from the cosmos. If dark matter particles annihilate or decay, they might produce neutrinos that could travel across the universe to reach detectors here on Earth. Experiments like IceCube, a massive neutrino detector built into the Antarctic ice, scan the sky for high-energy neutrinos that might originate from dark matter interactions in the cores of planets, stars, or galaxies. The beauty of indirect detection is that it can probe dark matter interactions across the entire observable universe. While direct detection experiments are limited to particles passing through Earth, indirect detection can search for dark matter signatures from the earliest galaxies, from galaxy clusters billions of light-years away, and from regions of space where dark matter densities are much higher than they are in our local neighborhood. But perhaps the most ambitious approach to dark matter detection involves creating these particles ourselves. This brings us to collider experiments, where scientists use the most powerful particle accelerators on Earth to recreate the conditions that might have produced dark matter in the early universe. The Large Hadron Collider at CERN, the world's most powerful particle accelerator, smashes protons together at energies approaching those that existed just moments after the Big Bang. In these high-energy collisions, entirely new particles can be created, including potentially the very dark matter particles we've been seeking. The challenge is that dark matter particles, by definition, don't interact strongly with the detector systems, so we can't see them directly. Instead, we have to look for their absence, missing energy and momentum that would indicate invisible particles have been produced and carried away energy that we can't account for. This technique has already been used to discover neutrinos, which were first detected as missing energy in particle decay processes. The same principle applies to dark matter searches at the LHC. When protons collide, they can produce a shower of known particles, along with potentially one or more dark matter particles. The visible particles are detected and measured, but if their total energy and momentum don't add up to what went into the collision, it suggests that invisible particles carried away the difference. The LHC experiments, ATLAS, CMS, LHCb, and ALICE, have been searching for these signatures for over a decade. They've set stringent limits on the properties of potential dark matter particles and have ruled out many theoretical models. While they haven't yet discovered dark matter directly, they've provided crucial information about what dark matter isn't, helping to guide theoretical development and other experimental approaches. Looking toward the future, even more powerful colliders are being planned. The proposed future circular collider would be 4 times larger than the LHC and could reach energies high enough to produce dark matter particles that are currently beyond our reach. These machines represent humanity's most ambitious attempts to recreate the conditions of the early universe and probe the fundamental nature of matter and energy. Each of these detection strategies, direct, indirect, and collider, offers unique advantages and faces distinct challenges. Direct detection experiments provide the most unambiguous evidence if they succeed, but they're limited to dark matter particles that interact through the weak nuclear force or similar mechanisms. Indirect detection can probe a wider range of dark matter models and look across the entire universe, but the signals are often ambiguous and difficult to distinguish from astrophysical backgrounds. Collider experiments can create dark matter particles with precisely known conditions, but they're limited by the energy scales they can reach and may miss dark matter that's too heavy or too weakly interacting to produce. The true power of the dark matter detection enterprise lies in the combination of these approaches. When multiple experiments using different techniques all point toward the same conclusion, we can have much greater confidence in the result. This is why the dark matter community maintain such a diverse portfolio of experiments, each one probing different aspects of the same fundamental mystery. The sophisticated instruments and techniques we've developed for dark matter detection have also led to unexpected discoveries and technological advances. Ultra-pure xenon detectors have applications in medical imaging and nuclear security. The cryogenic technologies developed for dark matter experiments have improved quantum computing and other cutting-edge technologies. The data analysis techniques used to distinguish dark matter signals from backgrounds have found applications in machine learning and artificial intelligence. But perhaps most importantly, these experiments represent humanity at its best. International collaborations involving thousands of scientists from dozens of countries, all working together to answer one of the most profound questions we can ask. What is the universe made of? The quest to detect dark matter has pushed the boundaries of technology, engineering, and human ingenuity. It has taught us to think creatively about problems that seem impossible and to persist in the face of decades of null results. As we stand on the threshold of potentially discovering dark matter, it's worth reflecting on what that discovery would mean. Finding dark matter wouldn't just solve one of the greatest mysteries in physics. It would open up entirely new realms of science and technology. Understanding the properties of dark matter particles could lead to new forms of energy, new materials, and new ways of probing the universe. It might even provide clues about other deep mysteries, like the nature of dark energy or the possibility of extra dimensions. The search for dark matter continues, with each experiment pushing the boundaries of sensitivity, and each null result providing valuable information about what dark matter isn't. Somewhere in the data being collected right now, in underground laboratories and space-based telescopes around the world, might be the first clear signal of dark matter interaction. Or perhaps dark matter will reveal itself in a way we haven't yet imagined, through experiments we haven't yet conceived. What we know for certain is that the universe still holds profound secrets, and the search for dark matter represents one of our most ambitious attempts to uncover them. In pursuing these invisible particles, we're not just trying to solve a scientific puzzle. We're trying to understand our place in a cosmos that is far stranger and more wonderful than our ancestors ever imagined. We've already witnessed how dark matter shapes the cosmic web and eludes our most sophisticated detectors. But now we venture deeper into the theoretical landscape where scientists propose specific candidates for these mysterious particles. Each candidate represents not just a mathematical possibility, but a potential key to unlocking one of the universe's greatest secrets. At the forefront of this search stand WIMPs, or weakly interacting massive particles. These theoretical entities have captured the imagination of physicists for decades, primarily because they emerge naturally from many extensions of the standard model of particle physics. Think of WIMPs as the universe's most elusive guests at a cosmic party. They're everywhere around us, but they barely interact with the ordinary matter that makes up everything we can see and touch. This refers to the remarkable observation that particles with masses and interaction strengths typical of electroweak physics naturally produce the observed abundance of dark matter in the early universe. It's as if the universe was designed with a perfect recipe. Add the right amount of mass, sprinkle in just enough interaction strength, and voila, you get exactly the amount of dark matter we observe today. Supersymmetry, one of the most elegant theoretical frameworks in particle physics, provides a natural home for WIMP candidates. In supersymmetric theories, every known particle has a heavier partner. The photon has a photino, quarks have squarks, and electrons have selectrons. The lightest of these supersymmetric particles, often called the neutrino, would be stable and interact only weakly with ordinary matter, making it an ideal dark matter candidate. But here's where the story takes an intriguing turn. Despite decades of increasingly sophisticated searches, no definitive WIMP signal has been observed. underground detectors buried deep within mountains, space-based telescopes scanning for the gamma rays that WIMPs might produce when they annihilate, and particle accelerators attempting to create WIMPs in high-energy collisions have all come up empty-handed. This absence of evidence has led some researchers to speak of a growing crisis in dark matter research. Yet this apparent setback has opened doors to other fascinating possibilities. Enter Axions, particles originally proposed to solve an entirely different problem in particle physics. These hypothetical entities were conceived to address the strong CP problem in quantum chromodynamics, but they've found a second life as dark matter candidates. Unlike WIMPs, Axions would be incredibly light and numerous, forming a kind of cosmic ocean of dark matter that pervades the universe. The search for Axions requires entirely different experimental approaches. The Axion Dark Matter Experiment, or ADMX, represents one of the most ingenious attempts to catch these elusive particles. Picture a microwave cavity sitting inside a powerful magnetic field. If Axions exist and are passing through this setup, they should occasionally convert into photons that the experiment can detect. It's like trying to catch whispers from the cosmos using the most sensitive listening devices we can build. Then there are sterile neutrinos, particles that take the already mysterious world of neutrinos and make it even stranger. While ordinary neutrinos barely interact with matter, sterile neutrinos would be even more aloof, communicating with the rest of the universe only through gravity and perhaps through mixing with their ordinary cousins. These particles could potentially explain both the dark matter mystery and several puzzling observations in neutrino physics. Recent years have also seen a resurgence of interest in primordial black holes as dark matter candidates. These aren't the black holes formed from collapsed stars, but rather ancient gravitational wells that might have formed in the early universe from extremely dense regions of matter. The discovery of gravitational waves from black hole mergers has rekindled interest in these primordial objects, especially since they could potentially account for the entire dark matter abundance, while avoiding some of the detection challenges faced by particle candidates. What makes primordial black holes particularly intriguing is their potential connection to the supermassive black holes we observe at the centers of galaxies. If these primordial objects existed in the early universe, they could have served as the seeds around which the first stars and galaxies formed, helping to explain how such massive structures appeared so early in cosmic history. The experimental landscape for dark matter detection continues to evolve rapidly. Direct detection experiments like Lux-Zeppelin push the boundaries of sensitivity, searching for the tiny signals that dark matter particles might produce when they occasionally collide with ordinary matter. Indirect detection efforts scan the skies for the radiation that dark matter might produce when particles annihilate with each other, and collider experiments attempt to create dark matter particles in high-energy crashes between protons. Each approach offers unique advantages and faces distinct challenges. Direct detection experiments must contend with incredibly low interaction rates and the need to distinguish genuine dark matter signals from background radiation. Indirect detection requires understanding complex astrophysical environments where dark matter signals might be produced, and collider experiments must create conditions similar to those in the early universe while interpreting the complex particle interactions that result. The diversity of dark matter candidates and detection methods reflects both the richness of theoretical physics and the profound mystery we're trying to solve. Whether dark matter consists of WIMPs floating through underground detectors, axions converting to photons in magnetic fields, sterile neutrinos mixing with ordinary ones, or primordial black holes warping space-time, the answer will fundamentally change our understanding of the universe. Perhaps most remarkably, we're living through a time when these questions might actually be answered. The next generation of experiments promises unprecedented sensitivity to dark matter interactions, New theoretical insights continue to refine our understanding of how dark matter should behave and where we're most likely to find it. And advances in computational power allow us to simulate dark matter's behavior with ever greater precision. As we stand on the threshold of potentially discovering dark matter, we're reminded that some of the universe's greatest secrets might be hidden in the spaces between atoms, in the silent depths of underground laboratories, or in the subtle signals arriving from distant galaxies. The search for dark matter represents more than just a quest to identify mysterious particles. It's a journey toward understanding the very foundation of cosmic structure and our place within it. The candidates we've explored today each tell a different story about how the universe might work at its most fundamental level. Now we arrive at one of the most sophisticated chapters in our dark matter detective story, where the hunt for these elusive particles has led us deep underground, far from the bustle of everyday life, into some of the quietest, most pristine laboratories ever constructed. These aren't your typical research facilities with humming computers and fluorescent lights. Instead, they're carved into mountainsides, buried beneath miles of rock, shielded from the cosmic rain that constantly peppers our planet from space. Picture this, if you will. Nearly a mile beneath the Black Hills of South Dakota, in what was once the home state gold mine, scientists have built one of the most sensitive dark matter detectors on Earth. It's called Elusive Zeppelin, or LZ for short, and it represents the cutting edge of our attempts to catch dark matter in the act. Down there in the cool darkness, surrounded by ancient rock formations, sits a vessel filled with liquid xenon so pure it makes the cleanest laboratory chemicals look positively grimy by comparison. The whole setup has an almost mystical quality to it. Imagine a great metallic shrine, carefully assembled in a cathedral of stone, waiting patiently for the whisper of a dark matter particle. The xenon, cooled to minus 160 degrees Fahrenheit, sits perfectly still, monitored by hundreds of photosensors that can detect the faintest glimmer of light. These sensors are so sensitive they could spot a single photon, like seeing a lone firefly in a vast moonless night. But why go to such extraordinary lengths? Why bury these experiments so deep underground? The answer lies in the simple fact that space is constantly showering our planet with particles. Cosmic rays, high-energy particles from distant stars and galaxies, are continuously bombarding Earth's atmosphere. When they hit, they create cascades of secondary particles that rain down on us every second of every day. Most of these pass through us harmlessly, but they would create a tremendous amount of noise for any detector trying to spot the subtle signature of dark matter. Think of it like trying to hear a whispered conversation in the middle of a thunderstorm. The cosmic ray particles are the thunder, drowning out the gentle murmur of dark matter interactions. By going deep underground, scientists use the Earth itself as a shield. Miles of solid rock filter out nearly all of these cosmic intruders, creating an environment so quiet that even the most delicate dark matter collision might finally be heard. The beauty of these underground sanctuaries extends beyond just their practical purpose. There's something deeply contemplative about the idea of scientists descending into the Earth's depths, like modern-day miners not seeking gold or coal, but hunting for the fundamental building blocks of the universe. In these subterranean laboratories, time moves differently. The usual markers of day and night disappear, replaced by the steady rhythm of data collection and the patient wait for discovery. The LUX experiment, LZ's predecessor, spent years in this underground vigil. For over 3 years, it watched and waited, recording every tiny interaction in its xenon target. Scientists analyzed petabytes of data, searching for the telltale signature of a dark matter particle colliding with a xenon nucleus. The signature they're looking for is incredibly specific. A tiny flash of light followed by a small electrical signal with just the right energy and timing to distinguish it from the background noise of radioactive decay and other mundane interactions. But here's the beautiful paradox of this search. The very thing that makes dark matter so mysterious is what makes it so hard to detect. Dark matter particles, if they exist as most theories predict, interact with ordinary matter only through gravity and possibly the weak nuclear force. This means they can pass through entire planets without batting an eyelash. Every second, millions or perhaps billions of dark matter particles may be streaming through your body, through the Earth, through these underground detectors, without leaving so much as a ripple. The odds of catching one are extraordinarily small. Imagine trying to catch a specific raindrop in a thimble during a gentle drizzle. Except the raindrops are invisible and pass through the thimble most of the time. This is why these detectors need to be so large and run for so long. They're playing a numbers game, hoping that eventually, just occasionally, one of these phantom particles will interact with their carefully prepared target. And yet, despite years of patient observation, despite the exquisite sensitivity of these underground sentinels, the results have been puzzling. Eludes saw no definitive signs of dark matter, neither have most of the other underground experiments around the world. From the xenon detector deep beneath Italy's Gran Sasso mountain to the Panda experiment in China's Jinping underground laboratory, the story has been largely the same. Lots of beautiful, clean data, but no smoking gun evidence for dark matter particles. This might sound discouraging, but in the world of particle physics, negative results are often just as valuable as positive ones. Each experiment that fails to detect dark matter helps narrow down the possible properties these particles might have. They're telling us that if dark matter particles exist, they must be even more elusive than we initially thought. They must interact even more weakly with ordinary matter, or perhaps they have masses or properties quite different from our current best guesses. The next generation of these underground experiments promises to be even more sensitive. Lux Zeppelin, with its larger target mass and improved shielding, can probe deeper into the possible hiding places of dark matter. Other experiments are trying different approaches entirely. Some use different target materials, like germanium or silicon crystals, cooled to just a fraction of a degree above absolute zero. These cryogenic detectors can sense the tiny amount of heat generated when a dark matter particle bumps into an atomic nucleus, like feeling the warmth of a breath on your hand in a freezing room. There's something almost meditative about imagining these detectors in their underground chambers, waiting with infinite patience for a signal that may or may not come. They represent one of humanity's most ambitious attempts to eavesdrop on the universe's hidden conversations. In the profound silence of these subterranean laboratories, scientists are listening for the faintest whisper from the dark sector of reality. But the underground approach is just one strategy in our multi-pronged assault on the dark matter mystery. While some scientists burrow deep into the Earth, others are turning their gaze upward, using space-based telescopes and particle detectors to search for the signatures of dark matter annihilation in the cosmos. Still others are trying to create dark matter particles in powerful accelerators, smashing ordinary particles together with such tremendous energy that they might briefly bring dark matter into existence. Each approach offers its own unique perspective on the puzzle. The underground detectors excel at looking for dark matter particles that interact directly with ordinary matter. Space-based experiments can search for the gamma rays or other particles that might be produced when dark matter particles collide and annihilate each other in the depths of space. Accelerator experiments can probe whether dark matter might be created in high-energy collisions, even if it immediately escapes detection. As you settle deeper into your evening routine, perhaps there's something comforting in knowing that far beneath the Earth's surface, these patient guardians continue their vigil. In chambers carved from living rock, surrounded by the weight of mountains, sophisticated instruments wait with mechanical patience for a signal from the universe's hidden realm. Whether they find what they're looking for or continue to return empty-handed, they're pushing the boundaries of human knowledge, one careful measurement at a time. The underground dark matter experiments represent more than just sophisticated technology. They embody our species' relentless curiosity about the fundamental nature of reality. In these deep, quiet places, removed from the chaos of the surface world, we're conducting one of the most important conversations in the history of science, a dialogue with the universe itself about what it's truly made of. The future of dark matter research stands at an extraordinary crossroads, where humanity's most sophisticated tools are finally beginning to catch whispers from the invisible universe. After decades of increasingly sensitive searches, yielding tantalizing hints but no definitive discoveries, we find ourselves in what some researchers call the end game of traditional dark matter detection. The next generation of experiments promises to push our technological limits to their absolute boundaries. The LUX Zeppelin detector, successor to the groundbreaking LUX experiment, represents a quantum leap in sensitivity. This massive underground instrument, containing over 7 tons of ultra-pure liquid xenon, can detect interactions so subtle that they occur perhaps once in a trillion collisions. It's like listening for a whisper in a thunderstorm, except the whisper might hold the key to understanding 85% of all matter in existence. But LZ is just one voice in a growing chorus of detection methods. The Euclid Space Telescope, launched in 2023, is mapping the cosmic web with unprecedented precision, tracing dark matter's gravitational fingerprints across billions of light years. Meanwhile, the Vera Rubin Observatory will soon begin its legacy survey of space and time, photographing the entire visible sky every few nights for a decade, watching how dark matter shapes the dance of galaxies across cosmic time. Perhaps most intriguingly, we're entering an era of multi-messenger dark matter astronomy. Just as gravitational wave detectors opened an entirely new window on the universe, future experiments may catch dark matter through multiple channels simultaneously. Imagine detecting a dark matter particle interaction in an underground laboratory at the exact moment that space-based telescopes observe a corresponding gamma ray burst from the same region of sky. Such coordinated observations could finally provide the smoking gun evidence that has eluded us for so long. The technological innovations emerging from this quest are remarkable in their own right. Scientists are developing quantum sensors so sensitive they can detect the motion of individual atoms. They're creating materials with properties that seem almost magical, like aerogels, so light they barely interact with ordinary matter, yet dense enough to stop the most elusive particles. Some experiments are even exploring whether dark matter might be detected through its effects on atomic clocks, turning time itself into a dark matter detector. Yet for all these technological marvels, perhaps the most exciting developments are theoretical. New models suggest dark matter might not be a single type of particle, but an entire dark sector, a hidden universe of particles and forces as rich and complex as our own visible world. Some theories propose dark atoms, dark chemistry, even dark planets, orbiting dark stars in galaxies we can never see directly. If true, this would mean we're not just searching for one missing piece of the cosmic puzzle, but discovering that the puzzle itself is far larger and more intricate than we ever imagined. The implications extend far beyond academic curiosity. Understanding dark matter could revolutionize our grasp of fundamental physics, potentially revealing new forces, new dimensions, or entirely new principles governing reality. Some theoretical frameworks suggest that dark matter research might even shed light on the deepest mysteries of quantum mechanics and gravity, bridging the gap between the universe's smallest and largest scales. As detection technologies become more sophisticated, we're also learning to ask more nuanced questions. Rather than simply asking what is dark matter, we're beginning to explore how it behaves, how it formed in the early universe, and how it continues to shape cosmic evolution today. Some of the most promising research focuses on dark matter substructure, the possibility that dark matter forms complex patterns and hierarchies that mirror, but don't exactly match, the structures we see in ordinary matter. Looking ahead, the next decade may well be remembered as the moment when humanity finally glimpsed the dark universe that surrounds us. Whether through direct detection, indirect observation, or theoretical breakthrough, we stand on the threshold of potentially the greatest scientific discovery since the realization that the universe is expanding. And as we peer deeper into this cosmic mystery, we're reminded that the most profound questions often have the most beautiful answers, hidden just beyond the edge of what we thought was possible. Now we're diving into one of the most intriguing questions in modern physics. What exactly is dark matter made of? After decades of searching, we still don't have a definitive answer, but we do have some fascinating candidates that might solve this cosmic mystery. The leading contenders for dark matter particles span an enormous range of possibilities, each with their own theoretical motivations and experimental signatures. The most extensively studied class is known as WIMPs, or weakly interacting massive particles. This refers to the remarkable observation that particles with weak scale masses and interaction cross-sections naturally produce the observed dark matter abundance in the early universe through thermal processes. WIMPs emerged naturally from many extensions of the standard model of particle physics, particularly supersymmetric theories. In supersymmetry, every known particle has a heavier partner, and the lightest of these supersymmetric particles could serve as dark matter. The photino would be the partner of the photon, the squark the partner of the quark, and the selectron the partner of the electron. The lightest supersymmetric partner has the right properties to be a stable dark matter candidate. What makes WIMPs so appealing is their experimental accessibility. They should be detectable through direct detection experiments, where we look for their rare interactions with ordinary matter in highly sensitive underground laboratories. They could also reveal themselves through indirect detection, as their annihilation products might be observable in space-based telescopes. Additionally, they might be produced at particle accelerators like the Large Hadron Collider. However, after decades of increasingly sensitive searches, no definitive WIMP signal has been observed. This has led to what some researchers call a crisis in dark matter research. The most theoretically motivated candidates remain elusive despite enormous experimental efforts. There's a growing sense that we may need to look beyond the traditional WIMP paradigm. One particularly promising subclass of WIMP candidates that has recently gained attention is the Higgsino. This theoretical particle would be a heavier version of the Higgs boson, with a mass roughly 1,000 times greater than a proton. The Higgsino is arguably one of the most likely possibilities for dark matter because of its natural connection to the Higgs mechanism, which gives mass to particles in the standard model. Building on previous studies of lighter dark matter candidates, researchers have shown that the gamma-ray signal predicted from Higgsino collisions could be detected using the upcoming Cherenkov Telescope Array Observatory. According to some physicists, the Higgsino represents one of our last chances to discover the class of dark matter candidates called WIMPs that we've been pursuing for decades. But WIMPs aren't the only game in town. Axions represent a fundamentally different approach to dark matter, originally proposed to solve an entirely unrelated problem in quantum chromodynamics called the strong CP problem. The elegance of Axions lies in their ability to solve two major puzzles simultaneously: a technical issue in particle physics and the dark matter problem in cosmology. Unlike WIMPs, which would be produced through thermal processes in the early universe, Axions would be created through non-thermal mechanisms. They're predicted to have very low masses and interact extremely weakly with ordinary matter, making them difficult to detect. The theoretical mass range for axions spans many orders of magnitude, from ultralight fuzzy dark matter axions to heavier variants. The search for axions has led to some of the most sophisticated detection experiments in physics. The Axion Dark Matter Experiment, or ADMX, represents a fascinating exercise in contradictions. Scientists are trying to detect invisible dark matter by converting it into photons using powerful magnetic fields. The experiment operates in extreme cold to search for particles forged in the early universe's extreme heat. It uses microscopic devices to find a substance that comprises most of the mass of a galaxy. ADMX works by placing a microwave cavity inside a powerful magnetic field. Any axions passing through would be converted into detectable microwave photons. The experiment has already excluded portions of the axion mass range and continues to push toward greater sensitivity. Unlike the searches for WIMPs, which have plenty of international competition, ADMX stands nearly alone as a large-scale hunter for axions. The upgraded ADMX Gen 2 configuration promises significantly enhanced sensitivity through the addition of a dilution refrigerator that reduces the temperature of the cavity and receiver. This lower temperature will result in an experiment that, over its 3-year operation, could be sensitive to even weakly coupled axions over a large fraction of their plausible mass range. Many in the physics community believe ADMX Gen 2 has serious discovery potential. Another intriguing class of candidates is sterile neutrinos. Unlike the 3 known active neutrinos that participate in weak interactions, sterile neutrinos would interact only through gravity and possibly through mixing with active neutrinos. This minimal interaction makes them excellent dark matter candidates, while simultaneously providing a potential explanation for the observed masses of active neutrinos. Sterile neutrinos, with masses in the keV range, could constitute warm dark matter, potentially affecting the formation of small-scale structure in the universe differently than cold dark matter. They might also produce observable X-ray lines from their decay, though the interpretation of these signals remains controversial within the scientific community. Perhaps the most radical departure from traditional particle dark matter is the idea that dark matter consists of primordial black holes. These hypothetical black holes would have formed in the early universe from extremely dense pockets of matter, not from stellar collapse like the black holes we observe today. Because they would predate the first stars, primordial black holes aren't limited to the narrow mass range of stellar black holes. The appeal of primordial black holes as dark matter candidates has grown significantly following LIGO's detection of gravitational waves from black hole mergers. 4 times the mass of our Sun, they could potentially account for all dark matter. These black holes could have served as seeds around which the first stars and galaxies formed, and they might even explain the origin of supermassive black holes. Recent theoretical developments suggest that primordial black holes might be stabilized by quantum effects, making them exactly the kind of purely gravitational dark matter that traditional detection methods couldn't find. While the full quantum mechanical treatment is still under development, the existence of primordial black holes could be proven or disproven in the near future through observations from the James Webb Space Telescope and future gravitational wave missions. The landscape of dark matter candidates reflects both the richness of theoretical physics and the challenge of detecting something that interacts so weakly with ordinary matter. Each candidate offers a different window into fundamental physics, from the electroweak scale probed by WIMPs to the quantum chromodynamics explored by Axions, from neutrino physics investigated through sterile neutrinos to quantum gravity examined through primordial black holes. What's remarkable is that after decades of searching, we're entering a period where multiple experimental approaches are reaching the sensitivity needed to potentially detect or rule out these candidates. The next few years may finally answer the question of what dark matter is made of, or they may push us toward even more exotic possibilities we haven't yet imagined. As we stand on the threshold of potentially discovering the nature of dark matter, we're reminded that the universe still holds profound secrets. The invisible substance that dominates the cosmos might be made of particles we've never seen, or it might challenge our understanding of physics in ways we haven't anticipated. Either way, the search for dark matter continues to push the boundaries of human knowledge and technological capability. The question of what dark matter is made of remains one of the greatest mysteries in science, but it's a mystery that we're closer than ever to solving. Now that we've explored the mysterious nature of dark matter and its various candidates, from WIMPs and Axions to sterile neutrinos and primordial black holes, we arrive at a critical juncture in our cosmic investigation. Each of these theoretical particles represents decades of careful scientific reasoning, yet none have yielded definitive detection despite increasingly sophisticated experimental efforts. This absence of concrete evidence has led the dark matter community to diversify their search strategies, creating what some researchers describe as the most comprehensive particle hunt in the history of science. The Large Underground Xenon Experiment, or LUX, exemplified the direct detection approach that dominated dark matter searches for over 2 decades. Deep beneath the Earth's surface, shielded from cosmic radiation and environmental interference, LUX waited patiently for the subtle collision between a dark matter particle and a xenon atom. The experiment represented a triumph of engineering precision, with photosensors capable of detecting individual photons and electronics sensitive enough to measure the faintest whisper of interaction. Yet after years of operation, achieving sensitivities that would have seemed impossible just decades earlier, LUX found nothing. No WIMP collisions, no mysterious signals, just the quiet hum of perfectly calibrated instruments detecting only the background radiation they were designed to ignore. This null result, rather than representing failure, actually advanced our understanding significantly. Each negative detection constrains the possible properties of dark matter particles, gradually narrowing the theoretical landscape and forcing physicists to reconsider long-held assumptions. The Lux-Zeppelin experiment, LUX's more sensitive successor, continues this methodical process of elimination, using even larger volumes of liquid xenon and more sophisticated detection methods to probe deeper into the possible parameter space of dark matter interactions. But direct detection represents only one front in the multi-pronged assault on the dark matter mystery. Indirect detection experiments take a fundamentally different approach, searching not for dark matter particles themselves, but for the products of their annihilation or decay. When dark matter particles collide and destroy each other, they should produce standard model particles that we can detect: gamma rays, neutrinos, antimatter particles, or other exotic signatures that might reveal their presence. Space-based telescopes like the Fermi Gamma Ray Space Telescope scan the cosmos for unusual gamma ray emissions from regions where dark matter should be concentrated, such as the centers of galaxies or the hearts of galaxy clusters. The appeal of indirect detection lies in its potential for dramatic discovery. Unlike direct detection experiments that must wait for rare interactions in carefully controlled laboratory conditions, indirect detection could potentially observe dark matter annihilation occurring throughout the universe on vast scales. Galaxy centers, where dark matter densities should be highest, become natural laboratories for observing these theoretical processes. Yet here too, despite years of observations and increasingly sophisticated analysis techniques, the signals remain tantalizingly elusive. The third major approach involves particle accelerators, attempting to create dark matter particles in high-energy collisions. The Large Hadron Collider at CERN regularly smashes protons together at energies approaching those present shortly after the Big Bang, potentially producing dark matter particles that would immediately escape detection, leaving only indirect evidence of their creation through missing energy in the collision debris. This approach offers the exciting possibility of not just detecting dark matter, but actually producing it under controlled conditions, allowing detailed study of its properties. Yet even the LHC, humanity's most powerful particle accelerator, has found no definitive evidence of dark matter production. Supersymmetric particles, which would provide natural dark matter candidates, remain absent from the experimental record. Each collision, each carefully analysed dataset, adds to our knowledge while simultaneously deepening the mystery. This systematic absence of detection across multiple experimental approaches has led to what researchers call the crisis in dark matter physics. The most theoretically motivated candidates, WIMPs in particular, should have been detected by now given the sensitivity of modern experiments. This crisis has sparked intense debate about whether we're looking in the wrong places, using the wrong methods, or perhaps fundamentally misunderstanding the nature of dark matter itself. Some physicists argue that we need to expand our search beyond the traditional WIMP paradigm. Ultralight dark matter, sometimes called fuzzy dark matter, might interact so weakly with ordinary matter that it requires entirely different detection strategies. These particles might be detected through their gravitational effects on atomic clocks, or through subtle changes in the behavior of quantum systems. Other researchers suggest that dark matter might exist in a hidden sector of physics, interacting primarily with itself through forces we haven't yet discovered. The search has also expanded to include more exotic possibilities. Primordial black holes formed in the early universe from gravitational collapse rather than stellar evolution could account for some or all of dark matter without requiring new particles at all. These black holes would range from microscopic to planetary masses, potentially detectable through gravitational waves when they merge, or through their gravitational lensing effects on background starlight. As we stand at this crossroads in dark matter research, the field demonstrates both the persistence required for fundamental science and the intellectual humility necessary when confronting the universe's deepest mysteries. Each null result, each refined experiment, each theoretical innovation brings us closer to understanding one of the most profound questions in modern physics: whether dark matter consists of undiscovered particles, primordial black holes, or represents a fundamental misunderstanding of gravity itself. The search continues with undiminished intensity. The next generation of experiments promises even greater sensitivity and novel approaches. Underground detectors will grow larger and more sophisticated. Space-based telescopes will probe deeper into cosmic history, and accelerators will push to higher energies. Each represents humanity's determination to illuminate the dark components of our universe, to understand the invisible scaffolding upon which all visible structure depends. In this grand scientific endeavor, every measurement matters, every theoretical insight contributes, and every experimental challenge overcome brings us closer to one of the most significant discoveries in the history of science. So here we find ourselves at the intersection of the impossible and the inevitable, where dark matter both shapes the universe and eludes our every attempt to grasp it. We've journeyed through underground laboratories and space observatories, through theoretical frameworks and particle accelerators, through the failed searches and refined parameters that have defined decades of scientific pursuit. We've seen how this invisible majority governs the formation of galaxies, the structure of the cosmic web, and the very evolution of everything we observe, yet remains stubbornly hidden from direct detection. What emerges from this exploration isn't frustration, but fascination. The null results from experiments like Lux and Xenon haven't diminished our understanding of dark matter. They've sharpened it, carving away impossible territories and focusing our search on ever more precise possibilities. Each non-detection tells us something valuable about what dark matter isn't, gradually sculpting the parameter space where it might hide. It's a process as much about elimination as discovery, as much about patience as breakthrough. The diversity of our search strategies reflects the profound uncertainty that still surrounds this cosmic mystery. WIMPs with their theoretical elegance, Axions with their dual role in solving particle physics puzzles, sterile neutrinos bridging active and passive worlds, primordial black holes offering a completely different paradigm. Each represents a different conversation with the universe, a different way of asking the same fundamental question. What is this invisible scaffold upon which everything else rests? Perhaps most remarkable is how dark matter research exemplifies the collaborative nature of modern science. Underground detectors require international cooperation. Space missions demand decades of planning and execution. Theoretical work builds upon generations of accumulated knowledge. The search for dark matter isn't just about finding a particle or confirming a theory. It's about humanity's collective effort to understand our place in the cosmos, to decode the language of gravity and structure that speaks in wavelengths we cannot see and forces we can barely measure. The experiments continue to grow more sensitive, the theories more sophisticated, the observations more precise. The Eludes Zeppelin detector pushes into unexplored parameter space. The Euclid mission maps dark matter's gravitational fingerprints across cosmic time. The James Webb Space Telescope peers into the early universe, where dark matter first began its patient work of construction. Each new instrument, each refined measurement, each theoretical insight adds another piece to this vast puzzle. And maybe that's the beauty of it. Dark matter reminds us that the universe still holds secrets, that there are discoveries yet to be made, mysteries yet to be solved. In an age where it sometimes feels like all the great questions have been answered, dark matter stands as a humbling reminder that we've barely scratched the surface of cosmic understanding. 85% of all matter remains unknown to us, a vast territory of ignorance that's simultaneously daunting and exhilarating. The next breakthrough might come from an underground laboratory in South Dakota, a satellite observatory orbiting Earth, or a theoretical insight scribbled on a whiteboard in a university somewhere. It might be a WIMP finally revealing itself in a flash of scintillation light, an axion converting to a photon in a magnetic field, or something entirely unexpected that forces us to rewrite our understanding of the cosmos. The beauty of scientific discovery is that we never know where or when the next revelation will emerge. So tonight, as you look up at the stars, remember that what you see, the glowing points of light, the sweep of the Milky Way, the distant galaxies barely visible to the naked eye, represents only a small fraction of what's actually there. The universe is filled with something else, something invisible and patient and quietly fundamental, something that was there before the first stars ignited and will remain long after they fade. Dark matter is the universe's greatest secret, and we're still learning how to ask the right questions. The search continues, as it must, driven by curiosity and wonder, and the irresistible human need to understand. Somewhere in the dark, answers are waiting. And perhaps that's enough. The knowledge that the mystery remains, that there are still frontiers to explore, that the universe keeps a few secrets, even from its most persistent admirers. In the end, dark matter isn't just about missing mass or invisible particles. It's about the enduring power of questions that matter, problems that challenge us, and the quiet confidence that eventually, with patience and ingenuity, and a little cosmic luck, we'll find our way to the truth. The dark matter is still out there, still shaping space and time, still holding galaxies together with its gentle, invisible hands. And we're still here, still watching, still wondering, still reaching toward understanding. The detection landscape represents one of the most sophisticated and technologically demanding frontiers in modern physics, where scientists deploy an arsenal of ingenious methods to catch dark matter particles that may be streaming through our laboratories right now. These experiments push the boundaries of sensitivity, requiring isolation from cosmic rays, cooling to near absolute zero, and detection systems so precise they can register the energy deposited by a single particle interaction. Direct detection experiments like the Large Underground Xenon experiment and its successor Lux-Zeppelin represent the gold standard in WIMP hunting. These detectors, housed deep underground to shield from cosmic radiation, use tanks of ultra-pure liquid xenon as both target and detector medium. When a dark matter particle collides with a xenon nucleus, it should produce both light and ionization signals that can be measured with exquisite precision. The LZ detector, with its 7 tons of active xenon, can detect interactions so rare they might occur only once per year per kilogram of detector material. The underground laboratories hosting these experiments are marvels of engineering in themselves. The Samford Underground Research Facility in South Dakota sits nearly a mile beneath the surface, shielded by billions of tons of rock that filter out cosmic rays while allowing dark matter particles to pass through unimpeded. The environment is so pristine that researchers must account for trace radioactivity from the concrete walls and even the natural radioactivity in their own bodies. But direct detection is just one prong of the attack. Indirect detection experiments take a completely different approach, searching for the products of dark matter annihilation rather than the particles themselves. When 2 dark matter particles collide and annihilate, they should produce standard model particles that we can detect. The Fermi Gamma Ray Space Telescope scans the sky for excess gamma rays that might indicate dark matter annihilation in the dense cores of galaxies or in the halos surrounding galaxy clusters. Ground-based experiments like the high-energy stereoscopic system in Namibia use arrays of telescopes to detect Cherenkov radiation produced when high-energy gamma rays strike Earth's atmosphere. These experiments have mapped the gamma ray sky with unprecedented precision, searching for the telltale signatures of dark matter decay or annihilation. The fact that they haven't found definitive signals places increasingly stringent limits on how dark matter might interact with itself and with ordinary matter. Particle accelerators represent the third major approach to dark matter detection. The Large Hadron Collider at CERN doesn't just search for new particles directly. It looks for missing energy in collision events that might indicate dark matter production. When protons collide at nearly the speed of light, they can create dark matter particle pairs that escape the detector without leaving a trace. The missing energy carried away by these invisible particles shows up as an imbalance in the collision debris, providing indirect evidence for dark matter production. The technological challenges facing these experiments are staggering. Direct detection experiments must discriminate between potential dark matter signals and backgrounds that can mimic them. A cosmic ray striking the detector, radioactive decay in nearby materials, or even seismic vibrations can produce false signals. Scientists have developed sophisticated analysis techniques using machine learning and statistical methods to separate genuine signals from noise. One of the most ingenious aspects of modern dark matter detection is the use of multiple target materials. Different dark matter candidates would interact preferentially with different types of nuclei. Some experiments use xenon, others use argon, germanium, or even more exotic materials like calcium tungstate crystals. By comparing results across different detector technologies, scientists can cross-check their findings and rule out systematic errors. The null results from these experiments, while disappointing to some, are scientifically invaluable. Each non-detection allows researchers to rule out entire classes of dark matter models and narrow the search space for future experiments. The parameter space for WIMP dark matter has been squeezed dramatically over the past 2 decades, forcing theorists to consider more exotic possibilities or to accept that dark matter might be far more elusive than originally hoped. Emerging technologies promise even greater sensitivity in the coming decade. Next-generation detectors will use noble liquids on unprecedented scales, with some proposals calling for detectors containing hundreds of tons of active material. New techniques like quantum sensors and superconducting detectors may open entirely new windows into the dark sector. The international nature of dark matter research reflects the magnitude of the challenge. Experiments involve collaborations spanning dozens of countries and hundreds of scientists. The sharing of techniques, technologies, and expertise across these collaborations has accelerated progress and ensured that the most promising approaches receive adequate resources and attention. Perhaps most remarkably, these detection efforts have revolutionized our understanding of the cosmos, even in the absence of a definitive dark matter discovery. The technologies developed for dark matter detection have found applications in medical imaging, national security, and fundamental physics research. The ultra-low background techniques pioneered by dark matter experiments have enabled new searches for neutrinoless double beta decay and other rare processes. As we stand on the threshold of potentially revolutionary discoveries, the detection landscape continues to evolve rapidly. Each new experiment pushes sensitivity further. Each null result constrains the possibilities more tightly, and each technological advance opens new avenues for exploration. Here we are now at the heart of our cosmic exploration, dear sleepy scientists, as we venture into one of the most profound mysteries of our universe. We've wandered through gravitational waves and cosmic microwave background radiation, traced the dance of galaxies and the behavior of black holes. Yet there remains something far more elusive, something that comprises most of the matter in our cosmos but refuses to be seen, touched, or directly detected. Tonight, we drift into the enigmatic realm of dark matter, that invisible scaffolding upon which all visible reality hangs. Picture this, if you will. You're sitting in your garden on a clear evening, gazing up at the Milky Way, stretching across the sky like a river of starlight. Every star you see, every galaxy twinkling in the distance, every planet and nebula captured by our most powerful telescopes, all of this represents less than 5% of what actually exists in the universe. The remaining 95% is hidden from us, composed of dark matter and dark energy, substances so mysterious that we know them primarily by what they are not. They don't emit light, they don't absorb light, they don't reflect light. They are the universe's greatest magic trick, present everywhere, yet invisible to our eyes and instruments. Dark matter, specifically, makes up approximately 27% of the universe, or put another way, about 85% of all matter. Think about that for a moment. In every cubic meter of space around you, in every breath you take, in every room you've ever occupied, dark matter particles are streaming through, perhaps billions of them every second, and yet you feel nothing. They pass through your body, through the earth, through entire stars, as if these solid objects were nothing more than gentle mist. It's rather like living inside a cosmic ghost story, where the spirits outnumber the living by more than 5 to 1. But how did we come to know about something we cannot see? The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky, a man with a wonderfully gruff demeanor who wasn't afraid to challenge the established order. Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity, when he noticed something peculiar. The galaxies within this cluster were moving far too quickly. According to the laws of physics and the amount of visible matter he could observe, These galaxies should have been flying apart long ago, scattered across the cosmos like leaves in an autumn wind. Yet there they were, held together in their cosmic dance. Zwicky calculated that there had to be about 400 times more matter present than what could be seen. He called this missing mass dunkel materie, or dark matter, coining the term that would puzzle scientists for nearly a century. At the time, his colleagues largely dismissed his findings. Perhaps his calculations were wrong, they suggested, or perhaps there was some conventional explanation they hadn't considered yet. But Zwicky was onto something profound. In the 1970s, astronomer Vera Rubin conducted observations that would cement dark matter as one of the greatest mysteries in cosmology. Rubin studied the rotation curves of spiral galaxies, measuring how fast stars orbit around their galactic centers. According to everything scientists understood about gravity and orbital mechanics, stars farther from the galactic center should move more slowly than those closer in, just as the outer planets in our solar system take longer to complete their orbits than the inner planets. But that's not what Rubin found. Instead, she discovered that stars throughout these galaxies were moving at roughly the same speed, regardless of their distance from the center. It was as if the galaxies were spinning like solid disks, rather than following the expected pattern. For this to be possible, there had to be enormous amounts of unseen matter providing the gravitational pull necessary to keep these distant stars moving so quickly. The galaxies were embedded in vast halos of dark matter, invisible cocoons of mass that extended far beyond the visible edges of the galaxies themselves. This discovery was revolutionary and unsettling in equal measure. It meant that our understanding of the universe was fundamentally incomplete. Everything we could see and measure, all the stars and planets and gas clouds that make up the cosmic landscape, were merely the tip of an enormous iceberg. The bulk of the universe's matter was hidden from us, its nature completely unknown. Since then, evidence for dark matter has accumulated from multiple independent sources, each pointing to the same inescapable conclusion. The universe is dominated by something we cannot directly detect. Gravitational lensing, the bending of light around massive objects, reveals the presence of dark matter by showing us how it warps the fabric of space-time. When astronomers observe distant galaxies through gravitational lenses, they can map the distribution of dark matter by studying how it distorts the images of background objects. The cosmic microwave background, that ancient afterglow of the Big Bang, carries within its subtle temperature fluctuations, the fingerprints of dark matter's influence on the early universe. Computer simulations of cosmic evolution can only reproduce the large-scale structure we observe today. The web-like distribution of galaxies and galaxy clusters, if they include vast amounts of dark matter to provide the gravitational scaffolding upon which ordinary matter could condense and form the first stars and galaxies. Yet despite decades of searching, dark matter remains stubbornly elusive. We know it's there because of its gravitational effects, but we have never directly detected a single dark matter particle. It's rather like trying to study an invisible person by watching how their footprints appear in snow, or how their presence affects the people around them. We can infer their existence, map their movements, even predict their behavior, but we cannot see them directly. This has led to one of the most ambitious scientific quests of our time. Deep underground, in laboratories shielded from cosmic radiation, scientists have built incredibly sensitive detectors hoping to catch dark matter particles as they stream through the Earth. In space, telescopes scan the cosmos for the telltale signs of dark matter annihilation or decay. At particle accelerators like the Large Hadron Collider, physicists smash protons together at enormous energies, hoping to create dark matter particles in the laboratory and observe their properties. But so far, dark matter has proven to be remarkably good at keeping its secrets. This has led some scientists to question whether our understanding of gravity itself might be incomplete, whether the phenomena we attribute to dark matter might instead be explained by modifications to the laws of physics on cosmic scales. It's a humbling reminder that despite our technological prowess and mathematical sophistication, the universe still holds mysteries that challenge our most fundamental assumptions about reality. As you drift off to sleep tonight, consider this remarkable fact. You are embedded in a cosmic ocean of dark matter, an invisible realm that shapes the structure of galaxies and the evolution of the universe itself. Every second, countless dark matter particles stream through your body, carrying with them the secrets of cosmic history and the fundamental nature of matter and energy. We live in a universe that is far stranger and more mysterious than our ancestors ever imagined. A cosmos where the invisible shapes the visible, where the unknown dominates the known. The search for dark matter continues, driven by humanity's irrepressible curiosity about the nature of existence itself. Perhaps tomorrow, or next year, or in the decades to come, we will finally solve this cosmic mystery, discover the true nature of dark matter, and add another chapter to our understanding of the universe. Until then, we remain cosmic detectives, following clues through the darkness, guided by the faint traces left by the invisible majority of our cosmos. And perhaps there's something beautiful in that mystery, in the knowledge that the universe still has so much to teach us. As you close your eyes and let sleep carry you away, remember that you are part of this grand cosmic story, a conscious observer in a universe where most of the matter remains hidden, waiting patiently for us to unlock its secrets. The quest to detect dark matter has reached a critical juncture where the absence of evidence is becoming as significant as evidence itself. After decades of increasingly sophisticated searches, the field finds itself at what many researchers describe as a crossroads. The most theoretically motivated candidates, WIMPs, Axions, and sterile neutrinos, remain stubbornly elusive despite enormous experimental efforts. This has prompted a growing re-evaluation of our approach and assumptions about the nature of dark matter. The WIMP paradigm, which has dominated dark matter research for over 3 decades, exemplifies this challenge. These weakly interacting massive particles emerged from extensions to the standard model of particle physics, particularly supersymmetric theories. The theoretical elegance of WIMPs lies in what's known as the WIMP miracle, the observation that particles with weak scale masses and cross-sections naturally produce the observed dark matter abundance through thermal production in the early universe. However, this theoretical beauty has not translated into experimental discovery. Underground detectors like Lux Zeppelin represent the pinnacle of direct detection technology. These experiments employed tons of ultra-pure liquid xenon, cooled to extreme temperatures and shielded deep underground to eliminate background radiation. When a WIMP strikes a xenon nucleus, it should produce a characteristic signal, a flash of light followed by ionization that can be precisely measured. The sensitivity of these detectors has improved by orders of magnitude over the past 2 decades, yet they continue to find nothing but silence where WIMPs should be whispering. The Large Hadron Collider has similarly failed to produce evidence of supersymmetric particles, further constraining the WIMP hypothesis. If dark matter consists of the lightest supersymmetric particle, as many theories predict, then the LHC should have been able to create these particles in high-energy collisions. The absence of such signals has pushed the viable mass range for many WIMP candidates into increasingly uncomfortable territory. This null result crisis has led to what some researchers call a nightmare scenario, a universe where dark matter interacts only through gravity, rendering it effectively undetectable by any means other than its gravitational effects. If this proves true, Direct and indirect detection experiments, no matter how sophisticated, will never reveal dark matter's identity. The technology would exist, the sensitivity would be sufficient, but the fundamental physics would render the quarry invisible. Yet the absence of evidence is not evidence of absence, and the dark matter community has responded to these challenges with remarkable creativity and determination. New theoretical frameworks have emerged, expanding the search beyond traditional WIMP models. Axions, originally proposed to solve the strong CP problem in quantum chromodynamics, have gained prominence as dark matter candidates. These ultralight particles would be produced non-thermally in the early universe and could form a fuzzy, dark matter component with distinctive properties on small scales. The Axion dark matter experiment represents a fundamentally different approach to detection. Rather than waiting for dark matter to collide with ordinary matter, ADMX attempts to convert axions into photons using powerful magnetic fields. The experiment operates at temperatures colder than deep space, listening for the faint microwave whispers that would signal axion to photon conversion. Recent upgrades have brought ADMX to the threshold of detecting even weakly coupled axions, potentially within reach of discovering dark matter through this entirely different mechanism. Sterile neutrinos offer yet another avenue for exploration. These hypothetical particles would interact only through gravity and mixing with active neutrinos, making them excellent dark matter candidates, while simultaneously explaining the observed masses of ordinary neutrinos. The search for sterile neutrinos spans multiple experimental approaches, from studying X-ray emissions from galaxy clusters to precise measurements of neutrino oscillations. Perhaps most intriguingly, primordial black holes have experienced a renaissance as dark matter candidates. The detection of gravitational waves from black hole mergers by LIGO and Virgo has renewed interest in the possibility that dark matter consists not of exotic particles, but of black holes formed in the early universe. These primordial black holes could span an enormous range of masses and would be detectable through their gravitational effects rather than particle interactions. The theoretical framework for primordial black hole dark matter has been enhanced by new understanding of quantum effects in black holes. Recent work suggests that these objects might be stabilized by quantum memory effects, preventing them from evaporating through Hawking radiation as rapidly as previously thought. If this proves correct, primordial black holes could account for all of dark matter while remaining stable on cosmological timescales. The experimental landscape continues to evolve rapidly. Next-generation direct detection experiments like Darwin and Argo will push sensitivity to the neutrino floor, the point where coherent scattering of neutrinos becomes an irreducible background. Space-based telescopes like the James Webb Space Telescope are already providing new constraints on primordial black holes by studying the early universe. The upcoming laser interferometer space antenna will be sensitive to gravitational waves from primordial black hole mergers, potentially revealing a population of dark matter black holes. Indirect detection remains a vibrant field, with gamma-ray telescopes searching for the annihilation products of dark matter particles. The Cherenkov Telescope Array Observatory will soon begin operations with unprecedented sensitivity to gamma rays from dark matter annihilation. If dark matter consists of particles that can annihilate, these instruments may finally detect the telltale signals from the centers of galaxies or dark matter substructures. The theoretical landscape has also expanded dramatically. Alternative theories of gravity, such as modified Newtonian dynamics, continue to be tested against astronomical observations. While these theories face significant challenges in explaining the full range of dark matter phenomena, they serve as important tests of our assumptions about the nature of gravity and the need for exotic matter. Warm dark matter models, where dark matter particles have small but non-zero velocities, offer different predictions for small-scale structure formation. These models could potentially resolve some of the apparent discrepancies between cold, dark matter simulations and observations of small galaxies. sterile neutrinos with KV-scale masses represent one such warm dark matter candidate. Self-interacting dark matter models propose that dark matter particles interact not only gravitationally, but also through new forces among themselves. These interactions could help explain the apparent diversity of dark matter halo profiles observed in galaxies and galaxy clusters. The search for self-interacting dark matter requires different experimental approaches and theoretical frameworks than traditional WIMP searches. The connection between dark matter and dark energy has also become an active area of research. Some theories propose that these two mysterious components of the universe are related, potentially solving multiple cosmological puzzles simultaneously. Quintessence models, where dark energy evolves over time, could have implications for dark matter production and evolution. Machine learning and artificial intelligence are increasingly being applied to dark matter searches. These tools can identify subtle patterns in data that might escape traditional analysis methods, potentially revealing weak signals of dark matter interactions. AI-driven analysis of astronomical surveys may uncover new gravitational lensing signatures or identify previously unknown populations of dark matter substructures. The field has also embraced the concept of multi-messenger astronomy, combining information from gravitational waves, electromagnetic radiation, and neutrinos to study dark matter. The simultaneous detection of gravitational waves and gamma rays from neutron star mergers has already provided new insights into fundamental physics, and similar approaches may reveal dark matter signatures. Despite the challenges, the dark matter community remains optimistic and determined. The diversity of experimental approaches ensures that multiple avenues remain open for discovery. Theoretical advances continue to suggest new signatures and detection strategies. The technological capabilities of experiments continue to improve at a remarkable pace. The stakes could not be higher. Dark matter represents one of the most profound mysteries in modern science, touching on fundamental questions about the nature of matter, space, and time. Its discovery would revolutionize our understanding of the universe and potentially open new technological frontiers. The absence of discovery, while scientifically valuable, would force a complete reconceptualization of cosmology and particle physics. As we stand at this crossroads, the dark matter problem exemplifies both the power and the limitations of human knowledge. We have mapped the invisible scaffolding of the universe through gravitational effects, predicted its properties through sophisticated simulations, and built extraordinary machines to catch its whispers. Yet it remains tantalizingly beyond our grasp, a reminder that the universe still holds secrets that challenge our deepest understanding. The next decade will likely prove decisive for dark matter research. New experiments will either detect these elusive particles or push the sensitivity to theoretical limits that would effectively rule out large classes of candidates. The James Webb Space Telescope will probe the early universe when dark matter first began to shape cosmic structure. Gravitational wave detectors will listen for signals from primordial black holes. Underground laboratories will strain to hear the faintest echoes of dark matter collisions. Whatever the outcome, the search for dark matter has already transformed our understanding of the cosmos and pushed the boundaries of experimental technique and theoretical insight. It has revealed that most of the universe consists of substances unknown to terrestrial experience, forced us to question our assumptions about the nature of matter and gravity, and inspired technologies that benefit society far beyond their original purpose. The mystery of dark matter remains one of the greatest intellectual challenges of our time, a cosmic riddle that connects the smallest scales of particle physics to the largest structures in the universe. So tonight, dear listener, we find ourselves at the end of our gentle voyage through the cosmic darkness, having wandered through one of the universe's most profound mysteries. We've traced the paths of invisible matter, from the first puzzling observations of galaxy rotation curves to the sophisticated underground laboratories where scientists patiently wait for dark matter particles that may never come. We've seen how this elusive substance, making up roughly 85% of all matter in the cosmos, reveals itself only through its gravitational whispers. Like a cosmic puppeteer working behind black curtains, dark matter shapes the very architecture of reality, guiding the formation of galaxies, bending light around massive clusters, and leaving its fingerprints in the ancient glow of the cosmic microwave background. Along the way, we've met the theoretical candidates for dark matter's identity. The WIMPs, those weakly interacting massive particles that seem so promising for decades, yet continue to evade detection despite our most sensitive instruments. The Axions, originally proposed to solve an entirely different puzzle in physics, now offering an alternative path through the dark matter maze. The sterile neutrinos, ghostly particles that might bridge the gap between the standard model and the hidden sectors of reality. And the primordial black holes, ancient gravitational fossils from the universe's violent youth that could account for the missing mass without requiring exotic new physics. We've explored the ingenious methods scientists use to hunt for these invisible quarries. Deep underground, in repurposed mines and specially constructed caverns, liquid xenon detectors sit in perfect stillness, waiting for the telltale flash that would announce a dark matter collision. In space, telescopes scan the cosmos for the gamma rays that might signal dark matter particles annihilating in the hearts of distant galaxies. At particle accelerators, physicists smash protons together at tremendous energies, hoping to create dark matter particles in the laboratory and observe their immediate disappearance. Yet despite decades of searching, despite instruments of extraordinary sensitivity, despite theoretical frameworks of elegant sophistication, dark matter remains stubbornly hidden. This absence of discovery has led to what some researchers call a crisis in the field, forcing scientists to reconsider their assumptions and explore ever more creative possibilities. Perhaps dark matter consists not of single particle species, but of an entire dark sector, a parallel universe of matter that interacts with our world only through gravity. Perhaps it's not made of particles at all, but represents a modification to our understanding of gravity itself, requiring us to rewrite Einstein's equations on cosmic scales. Or perhaps the solution lies in directions we haven't yet imagined, waiting for insights that will seem obvious only in retrospect. The search for dark matter has pushed the boundaries of human ingenuity, driving the development of technologies so sensitive they can detect individual atomic collisions, so precise they can measure gravitational waves from black holes billions of light years away, so sophisticated they can map the three-dimensional structure of the observable universe. These efforts have not been in vain, even without a definitive dark matter detection. They have deepened our understanding of the cosmos, revealed new phenomena, and opened unexpected avenues of research. As we've seen, the mystery of dark matter is intimately connected to the broader questions of cosmic evolution. Without some form of additional gravitational influence, the universe we observe simply couldn't exist. Galaxies wouldn't have formed in the time available since the Big Bang. The cosmic web of structure that spans billions of light years wouldn't have emerged from the smooth conditions of the early universe. The very stars that light our night sky might never have ignited. This realization highlights one of the most humbling aspects of modern cosmology. The ordinary matter that makes up everything we can see and touch represents less than 5% of the universe's total content. We are, quite literally, minority constituents in a cosmos dominated by dark matter and dark energy, substances whose nature remains largely mysterious despite decades of intensive study. Yet there's something profoundly hopeful about humanity's response to this cosmic mystery. Rather than being discouraged by our apparent insignificance, we've doubled down on our efforts to understand the universe around us. We've built more sensitive detectors, developed more sophisticated theories, and launched more ambitious experiments. We've embraced the possibility that reality might be far stranger and more wonderful than we initially imagined. The search for dark matter also represents a beautiful example of international scientific collaboration. Researchers from dozens of countries work together on massive projects that span continents and decades. The data from underground detectors in Italy informs theoretical work in Japan. Observations from space telescopes built by European agencies guide experimental designs in American laboratories. The mystery of dark matter has united humanity in a common quest for understanding. As we look toward the future, new technologies and approaches offer fresh hope for solving the dark matter puzzle. Next-generation detectors will probe previously unexplored regions of parameter space. Advanced computational models will simulate cosmic evolution with unprecedented detail. Novel experimental techniques may reveal signatures of dark matter that previous searches couldn't detect. Perhaps most importantly, young scientists around the world are bringing fresh perspectives to these ancient questions. They're not bound by the assumptions and preconceptions that might limit more established researchers. They're developing new mathematical tools, proposing innovative experimental designs, and asking questions that previous generations might not have thought to ask. The resolution of the dark matter mystery, when it comes, will likely reshape our understanding of physics as fundamentally as the discoveries of quantum mechanics and relativity did in the 20th century. It may reveal new fundamental forces, new particles, or new principles that govern the behavior of matter and energy on cosmic scales. It may provide the key to unifying gravity with the other forces of nature, solving one of physics' most enduring challenges. But even if the answer proves different from what we currently expect, even if dark matter turns out to be something we haven't yet imagined, the search itself has already transformed our understanding of the universe. We've learned that reality is far more subtle and complex than it appears. We've discovered that the cosmos is filled with invisible influences that shape everything we see. We've realized that the story of the universe is still being written, with new chapters waiting to be discovered. As you drift towards sleep tonight, perhaps you can take comfort in the knowledge that somewhere in the darkness, particles of dark matter are passing through your room, through your body, through the earth itself, carrying with them the secrets of cosmic evolution. They've been traveling since the universe was young, witnessing the birth of the first stars, the formation of the first galaxies, the emergence of the cosmic web that spans the observable universe. These invisible travelers connect you to the deepest mysteries of existence. They remind us that we live in a universe far stranger and more wonderful than our everyday experience suggests. They whisper of hidden dimensions, unknown forces, and undiscovered laws of nature waiting to be revealed. The mystery of dark matter is not just a scientific puzzle to be solved, but an invitation to wonder, to question, to explore the unknown with courage and curiosity. It's a reminder that even in an age of smartphones and space telescopes, when we sometimes feel that everything has been discovered, the universe still holds secrets that challenge our understanding and inspire our imagination. So sleep well, fellow cosmic voyager, knowing that you are part of a universe filled with mystery and wonder. And perhaps in your dreams, you'll glimpse the hidden realm of dark matter, that invisible scaffold upon which all of reality is built, waiting patiently for us to discover its secrets and finally understand our true place in the cosmic story. The search continues, the mystery endures, and the universe keeps its secrets just a little while longer. But that's part of the beauty of it all. In a cosmos where dark matter remains hidden, there are still frontiers to explore, still questions to answer, still wonders waiting to be discovered. And that, perhaps, is the most comforting thought of all. Good night.